Well, welcome to the second talk in the 2022 SWOCC Geology Lecture Series. And once again, as you can see, I'm coming to you live from the new Geology Lab in Umpqua Hall. And I want to give you a quick reminder, because usually I forget this. Please remember that the chat box is available. If you have any questions for Dr. Brendan Riley, please type them in there and we will pose them to Brendan at the end of the talk today. We'll be continuing the series virtually in winter 2022. And I know that many of you will be disappointed with that, but there is a little bit of a silver lining to that. So one of the things that for years we've been trying to get Dr. Chris Goldfinger from OSU, and I'm sure many of you are familiar with him, to come down and give the annual Cascadia anniversary talk. Well, every year he has an annual USGS seismic meeting that conflicts with that. And since his seismic meeting is being held virtually, he agreed, since that's during the daytime, to join us on Wednesday, January 26th, the actual anniversary of the last great Cascadia event in 1700 at 7 p.m. to give the 17th annual Cascadia anniversary talk. So I know personally, I'm really looking forward to that. We also have a great climate change talk after that in the spring with Dr. Sean Davis from NOAA. He's going to give us lessons at the School of Hard Knocks from the ozone hole to global climate change on Tuesday, February 8th. And this is a reschedule from the before times, a talk that, again, can only happen if we host through the talk virtually. So due to travel and life and those kinds of things. And maybe in early March through a new speaker series that's being provided by a group called the American Geophysical Union, which literally is the largest geologic scientific organization. Basically, that group, AGU and Geological Society of America, are the huge ones. But because of the pandemic and the fact that they're just getting their series off the ground and beta testing it, they're only providing speakers virtually. So hopefully, I'm keeping my fingers crossed, we'll have 3 great talks that literally wouldn't happen if we couldn't deliver them solely on live stream winter term. Also, keep an eye out. We're looking at 2 special talks spring term as well. So I want to take a second, thank our sponsors, the college, our IT, media productions team, the mill, which actually media productions, thank you, Dallas, DB Western, the College Foundation, and especially the Ocean Discovery Program, because they bring us tonight's speaker through their Distinguished Speaker Series. And of course, all of you out there as well. And so for tonight, with the 26th UN Climate Change Conference wrapping up this week in the UK, tonight's talk, which includes data collected in Iceberg Alley, is probably as pertinent as ever, and the timing is exceptional. And I'm so pleased that Brendan agreed to speak to us this evening. And truthfully, I never really expected to host a talk that had both paleomagnetism and climate change in the title, but here we are. Dr. Riley received his PhD from Oregon State. So one thing is he's extremely familiar with our region, including having participated in the past, probably close to in the present and the future, numerous research cruises on OSU vessels out of Newport. At present, he is a postdoctoral researcher at Scripps Institution of Oceanography. And of the many projects he's affiliated with, one expedition, I must say, is probably the best acronym that I've ever seen. Cascadia HOPS. I'll let Brendan tell us more later if he chooses. Ladies and gentlemen, it's my pleasure to introduce to you this evening Dr. Brendan Riley on revealing rhythms of ice ages with paleomagnetism. Brendan?
Well, thanks, Ron, for that introduction. It's great to be here, and I'm excited to be back in Oregon, even if it's just virtual. Let's see, I'll share my screen here to bring my presentation up. So as Ron introduced, I'm going to be talking about the rhythms of ice ages and the paleomagnetic contributions to understanding that. And so I'll get into what that means before. And I'm here on behalf of the International Ocean Discovery Program in their lecture series. And so really happy to be representing them as well. The expedition that I'll be talking about, that we'll get to in a little bit, in which we were studying these ice age cycles, was a 2-month expedition to an area called Iceberg Alley, and it consisted of a couple dozen scientists on a ship, this drill ship that I'll talk about in a minute. So I really have to start off just by thanking all the people you see in this picture, especially these people here who have been very involved with this specific project that I'm going to talk about. It's a really incredible group of international scientists that I got to work with, all from different specialties and interests, and made for some really exciting science. The International Ocean Discovery Program today and at least my involvement with it has been largely revolved around the capabilities of this ship, the Geodi's Resolution, which is a drill ship dedicated to the scientific exploration of the seafloor. But the International Ocean Discovery Program and its predecessors have a very long history of making major contributions to our understanding of the Earth system. It all started back in the early 1960s with a project called the Mohole, which had hoped to drill through the crust of the seafloor to reach the mantle and sample the mantle. And so if you're interested in that, there's an article from Life magazine written by John Steinbeck, who was a participant on the first expedition of Project Mohole from 1961, where they detail not sampling the mantle, but rather studying marine sediments off the coast of California that were Miocene in age, or about 10 million years old. And the excitement of all that we could learn about Earth's history by accessing these deeper sediments and studying them. And so today, that program is in the form of the International Ocean Discovery Program, although there were a series of programs before it, including the Ocean Drilling Program and the Deep Sea Drilling Project. And here's a map that just shows all the locations that have been explored by scientific drilling since the early 1960s. And so each one of these holes had a different purpose of the scientific motivation of why we studied it. Some were looking at things like Earth's climate history. Some were looking at Earth's geomagnetic history. Some were looking at the igneous and tectonic processes that are important for the ocean basin. And more recently, some have started to look at microbial life that lives far below the seafloor. So lots of cool interdisciplinary topics about Earth science. So I'm going to just show this video, which I think I'm going to have to narrate because I don't think the sound will come through, but just to give you a sense of how these cores are recovered. Over here to the left, you can see the people on the rig floor tripping pipe or sending pipe down to the seafloor from the ship itself. And so here's the Geodi's Resolution. And here's an animation of what we're seeing over here, the tripping pipe. The pipe enters through the center of the ship through something called a moon hole, which is just an opening in the middle of the ship, and extends to the seafloor with a rotating drill bit. And then once the drill string reaches the seafloor, we shoot down a 10-meter length of plastic pipe, which then cores sediments on the seafloor, brings that 10 meters back up to the ship, in which we drill down a little bit further and then try to recover the next 10-meter section. And so this is what one of those 10-meter sections looks like when it comes up onto the ship for us to study. And so from my perspective, as one of the scientists that's involved with the International Ocean Discovery Program, this is where the real excitement happens, when the cores come up on deck and we split them in half and we put them out on the table. And so a lot of time is spent on the ship just looking at these cores, describing these cores, standing around the core table and discussing what we're seeing. A lot of our initial observations, our initial discoveries, and the conversations that we have that spur the eventual research topics that we go to pursue happen around this table. And so it can be really exciting to see these cores come up for the first time, often from areas of the ocean that we're sampling for the first time. Then when you're on the ship, the ship is a floating laboratory and can collect just an incredible amount of data on these sediment cores right off the bat. Here is the station that I work at. It's where I make paleomagnetic measurements on the cores, or looking at the magnetic properties of the sediments. We can take samples on the ship for other analyses. There are geochemistry labs. There are stations to look at the microfossils that are present in the core. So it's really incredible what can be done over the course of the 2 months, and both recovering these long records of Earth history from the seafloor, and also just collecting a huge amount of data on them right off the bat. And sometimes it can be kind of fun to be at sea too, just for the experience of it. On this expedition to offshore Antarctica, we were visited by numerous charismatic megafauna, as well as some pretty beautiful icebergs. So at this point, I usually like to just make a little plug for getting involved with the International Ocean Discovery Program. If you are a young scientist and you're interested in Earth history or marine geology, it can be a really great way to be exposed to new forms of research, to meet new scientists to work with, and there are lots of ways to get involved. So if there's anything in this talk that kind of spurs your interest in something that you'd like to become more involved with, please talk to me about it. I'm happy to talk more about that side of being involved with the International Ocean Discovery Program. But so the purpose of this talk is using magnetostratigraphy to learn more about the rhythms of Paleocene climate, or of the rhythms of the ice ages. And so I'm going to start off by just talking a little bit about some of the background of how paleomagnetism has contributed to our understanding of Paleocene climate. And so I figured I'd start with this animation here, which may just look like a mess of spaghetti, but this is a computer simulation of a reversal of the Earth's magnetic field. And you can see it starts off in one polarity pattern, kind of moves into this time period of complete chaos, and then regrows in the other configuration. And to me, this is one of the most exciting parts about being a geologist, is that we have this opportunity to learn about aspects of our Earth system that we would never have known just based on our historical observations, such as these really dramatic events of the Earth's magnetic field flipping its polarity like this. And one of the other things that I find pretty amazing too is that sediments that accumulate at the seafloor can hold a history of these geomagnetic changes in the alignment of the magnetic moments of specific minerals that get deposited on the seafloor. And so this plot that I have here on the screen right now was from a paper that came out in 1966. And so this wasn't the first paper that showed that you could record a magnetic field in a magnetic reversal in sediments. But it was the first paper to show how powerful that tool could be for stratigraphy, for understanding stratigraphy. And so what we're looking at is a collection of sediment cores from different areas of the Southern Ocean and their polarity pattern. And so where the cores are shaded black, that indicates that the magnetic measurements that these authors made indicated that the magnetic minerals are pointing to the North Pole, like we have today, and we call that normal polarity. Where it's shaded white, it indicates those magnetic minerals are pointing in the opposite direction, towards what we think of the South Pole today, and we call that reverse polarity. And so this paper was able to show two things. One, it was able to show that they could correlate all these sediment cores from distributed throughout the Southern Ocean in a way to each other that's totally independent of their environmental signals or their lithologic variability, but purely based on these geomagnetic changes. And the other thing that it showed that you could do was you could correlate to a independently dated time scale of these flips of the Earth's magnetic field. And so at this point in 1966, that independent timescale came from radiometric dating of volcanic rocks, which were also determined to have either normal or reverse polarity. And from a climate perspective, they also showed that the onset of glacial ice rafted sediments or sediments transported to icebergs to these sites occurred right near this one magnetic reversal. And today we know that magnetic reversal occurred right around the Plio-Pleistocene boundary, or around the time where we had the onset of the major ice ages. So this was just an incredible paper. It showed all sorts of cool things that you could do. So in addition to holding a history of the geomagnetic history, sediment cores also contain a history of Earth's paleoclimate. So I've been talking about these ice ages, or these ice age cycles, and one of the ways that we really know, that we really learned a lot about these ice ages and how they've come and gone over the course of the last few million years, is by studying the stable isotopes, or the Del 18O, of is recorded in these shells of foraminifera. So this is a benthic foraminifera, or a little protist that lives on the seafloor. It forms its shell, and the shell is a reflection of the ocean temperature and chemistry, and then that gets preserved in sediments for us to study, millions of years later. And so this Del 18O tells us two things. It tells us about the temperature of the deep ocean, and it also tells us about global ice volume. And so as a result, it tells us when the Earth was cold and there was lots of ice, and then when it was warm and there wasn't a whole lot of ice. So we're going to move forward a little bit now. So now in 1973, there was a famous paper that came out by Shackleton and Updike. And this was the first paper to do one of these paleomagnetic reconstructions in the same core as one of these delta 18O, or oxygen stable isotope of foraminiferal calcite reconstructions. And so here we're looking at depth in a core. This core is about 16 meters long. And so as we look down this way, we're looking further back in time. And so if we look at the paleomagnetic reconstruction, here the magnetic minerals are pointing in one direction, indicating normal polarity. And then as we get back to this point in the core, the Earth's magnetic field had flipped, and now we're looking at reverse polarity, or those magnetic minerals pointing towards the South Pole. And in the same time, we see these variations in oxygen isotope values from, this is plotted on a reverse axis, so from low values to high values. And the high values indicate more ice and colder temperatures. So you can go back and you can count these somewhat cyclic variations from ice age to interglacial to ice age to interglacial, and so on, back and forth. And so now we know that this reversal occurred about 774,000 years ago. That was the last time the Earth's magnetic field flipped. And in that time, we had 8 significant ice ages. And so that's pretty cool. And so that hasn't changed. What has changed over the time are the ages of these reversals. And so as we've developed better ways of dating, both radiometrically dating volcanic rocks, and then new methods to date sediment cores, the ages of these reversals have changed quite a bit, especially as we get further back in time. So this is missing its axis, but this is millions of years. So we're looking back about 3.5 million years here. But what's important about the stratigraphy of these magnetic reversals is, even though the absolute ages of them have changed as these timescales have evolved and we found better ways of dating the magnetic reversals, and that's still happening today, especially as we go further back in time, the ages of these magnetic reversals are still changing. Their relative stratigraphy relative to Earth's climate change has not changed. And so an example of that is This reversal here, this transition from reverse polarity to normal polarity that occurred around 1 million years ago, is always found in this prominent interglacial period as defined by Benthic Delitino, what we call marine isotope stage 31. And pretty much no matter where you go in the world and you look, if you can measure oxygen isotopes and you can measure the paleomagnetic signal, you'll find this reversal in marine isotope stage 31. So even though the age has changed according to the time scale that it's at, its relative stratigraphy has stayed the same. And it's this intercalibration between the magnetics and the climate signal that's allowed us to work even when we're unsure of the time scale itself, because we have that strong independent stratigraphy. So since these early studies that I've showed you, these data sets have come a long way. This is a pretty iconic data set in paleoclimate. It's the oxygen isotope evolution of the deep ocean over the last 5.5 million years. That's on this axis here. And then the bottom here, you see the changes in the polarity of the Earth's magnetic field. So at this point, each one of these magnetic reversals is pretty well dated and forms the initial backbone for the time scale of this oxygen isotope curve here, which is then further refined using some other methods. And so the first thing that you probably noticed when you looked at this is that there's this evolution in both the mean values as well as the amplitude of variation of this oxygen isotope curve as we move from the warmer Pliocene, where we have these less variable, and this is again a reverse axis, so lower values of oxygen 18, delta 18O. And then as we transition into the Pleistocene about 2.6 million years ago, we enter into the mean values indicate a colder world with more ice, and the variability becomes a lot greater, suggesting or indicating the intensification of these ice ages. And so you can see the variation of these ice ages and as they grow larger and larger and larger as we move closer to today. And today we're right here during this interglacial time we call the Holocene. But there's something else going on in this figure too that's a little harder to see visually, and it's a change in the frequency or the rhythm of which these ice ages are coming and going. And so if we look at just the last time period of normal polarity, which is the last 774,000 years, and we create this plot. And so what this plot is telling us is how much variability there is in the frequency band associated with these periods. So 100,000 years, 41,000 years, 23, and 19,000 years. And so you can think of this plot as the higher this peak is, the stronger the drum is beating at that rhythm. And so for the last 774,000 years, if you do this kind of analysis, you see really strong variability at 100,000 years, and less variability at 41 and 23 and 19. So this is different then. So if we do the same analysis, but we go back in time to when there was less variability in the ice ages before this magnetic reversal. So this is in a reverse period. It has a few of these normal short polarity intervals, but this is looking at 774,000 years to 2.6 million years ago. You can see that all that power or that rhythm is only really beating at this 41,000 year period. Quite different than the other. And so this has been a major question in understanding the past climate of Earth or the paleoclimate of Earth, is why there was this transition from a dominant 41,000 year period to a dominant 100,000 year period. But the fact that these rhythms are at very predictable periods, that itself isn't surprising. So that's related to changes in Earth's orbit. And so Earth's orbit varies in three predictable ways. One way it varies is in its eccentricity, or how elliptical the orbit is. And so that has a very characteristic beat of 100,000 years. It changes in its obliquity or tilt. and that has a very characteristic period of 41,000 years. And it varies in its precession or its wobble, and that varies at both 19 and 23,000 years. So the pacing of the ice ages is related to these orbital changes, and each one of these orbital changes has a different impact on both the amount of solar radiation the Earth receives, as well as the distribution of that solar radiation relative to the Earth's seasons. So now we're going to try to bring this all together and to think about ice age rhythms of the last 4 million years. And so here I've got plotted that benthic delta 18O record again, showing that transition from the warm Pliocene into the colder Pleistocene with our larger and larger ice ages as we move forward. And what I'm going to plot here is, you can think of this as like a plot that shows the evolution of the strength of that rhythm, or how loud the drum is beating in each one of these frequency bands. So this is the period associated with the eccentricity, or how elliptical the Earth's orbit is. The red dashed line here is the orbital forcing, or the forcing of the climate system. The black line is the climate system response. And so what you should take away from this is that Earth's climate system seems to be responding in a way that's decoupled to the forcing at this frequency, and that this 100,000 year period kicks off in a time period we call the mid-Pleistocene transition, and is strongest in this normal polarity chron, or in the latest Pleistocene, when these ice ages are most variable here. It's a little different when we think about the obliquity frequency band. So in the obliquity frequency band, this is the 41,000 year beat. The forcing of the climate system, this by the orbits, this red line, looks a lot like the response of the climate system up until about this transition, this same transition where you see the 100,000 year power come in. And then finally, when we think about the precession frequency band, the climate system only really seems to respond to the forcing after that transition that kicks off about 1.4 million years ago. And before that response is very muted, or potentially absent. You don't see that sort of variability. We can look at this a different way too. If we detrend that analysis to account for the change in the amplitude as we move forward in time here, more towards the present, you can see that in the precession frequency band, there is a response that looks like the forcing. It's just very muted. It's just very hard to see when you plot it up on its own. And so this is part of the question. So one question we had was, why was there this dominant 41,000 year period before this transition and 100,000 year period after? And the other is, why is there this missing precession rhythm in the early ice ages, like you see here? And so one way to explain that, well, there are a couple ways to explain it, and there are hypotheses out there that work to just work, or there are hypotheses that predict that potentially these early ice sheets, or these older ice sheets, were just more sensitive to the kind of forcing that erode from changes in Earth's tilt. Earth's tilt will change things like the summer duration. It'll change things like hemispheric gradients. But there's another hypothesis out there that's called the antiphase hypothesis. And so the reason why we're so interested in why there's no precession signal is that the precession, or the wobble of Earth and its orbit, has a really large effect on the intensity of the peak summer solar radiation. So basically how warm the summers get, which we think is really important for controlling these large ice sheets, especially land-based ice sheets. But the way that this works is that when the northern hemisphere is receiving is at its point in its orbit where it has the most intense summers, or is receiving the most intense solar radiation during the summertime, the southern hemisphere will actually experience its weakest summers. And the opposite's true too. So when the southern hemisphere is experiencing its most intense summers, the northern hemisphere has its weakest summers. And so the two hemispheres are, as a result, out of phase from each other, which is different than that 41,000 year period where they'd be in phase. And so I have this simple model to try to explain what that might mean for understanding the records that we might drill from the ocean. And so imagine, if you will, this is a very simple Earth, and climate is being driven only by just how intense the solar radiation is during the summertime. And we have two records. So I've gone out on the Geodies resolution, and I've drilled a record up here in the northern North Atlantic that's reflective of northern hemisphere climate, and one here in the southern Atlantic that's reflective of southern hemisphere climate. And so these two records would tell us that we have signals that, well, the signals will look like this, and the rhythm or the frequency bands, the periods associated with where that variability is concentrated in this 23 and 19,000 year period, which is associated with that wobble of Earth's orbit and the intensity which causes changes in the intensity of how warm the summers are. But because these signals are out of phase from each other in the different hemispheres, if I go out in the ocean and I find something that globally integrates that climate signal, that precession frequency band is canceled as a result of destructive interference, and we're only left with variability at the 41,000 year period. And so this global climate signal is effectively that benthic delta T0. So that's telling us about globally integrated ice volume in both hemispheres, and not changes in ice sheets in either the northern hemisphere or in the southern hemisphere. But we could effectively change that global climate signal if, say, for example, we make our northern hemisphere contribute more to the globally integrated signal, say by growing those northern hemisphere ice sheets to become even larger. Then some of that northern hemisphere signal won't get canceled out by the opposite southern hemisphere signal, and will increase the amount of precession in that globally integrated signal. So the antiphase hypothesis could suggest that perhaps that precession frequency is always there, or that precession signal is always there. It's just hidden in the globally integrated signal. And so a hypothesis that we could take away from that is that if we could isolate the signal associated with just one of the hemisphere's ice sheets, we might expect to see precession-paced variations where the globally integrated signal, this benthic delta T0, suggests that it's absent. And so this would be important because it would tell us that during this time period that our ice sheets were sensitive to the intensity of solar radiation during the peak solar radiation during the summertime. So to test this hypothesis, as well as some other cool ideas too, we went out in 2019 to drill in an area called Iceberg Alley, which is offshore Antarctica, in the hopes of getting one of these records that is reflective of just one of the hemisphere's ice sheets, just the Antarctic ice sheet. And so here's an animation that shows iceberg trajectories after they come off the Antarctic ice sheet. And where this white circle is here, this was the area that we were studying, that we drilled our cores in, this area called Iceberg Alley. And so it's called Iceberg Alley because when icebergs calve off the Antarctic continent, they often get trapped in this cold Antarctic coastal current that travels counterclockwise around the continent. And then we'll get caught in the Weddell Sea gyre and shot off into the Antarctic circumpolar current, which travels clockwise around the continent and is a warmer water mass. So these icebergs will melt in the Antarctic circumpolar current, and all the sediment that they're carrying from the Antarctic ice sheet will be deposited out in these areas. So by drilling here, we effectively get a record that is biased towards this sector of the ice sheet, but potentially carries signals of far-traveled icebergs from throughout the Antarctic ice sheet. Here's another look at our study area here. So the specific drill cores that I'll be talking about are from a basin within the Scotia Sea in Iceberg Alley called Dove Basin. And the sediments are deposits that we call, they're deep sea conturite deposits. And so they're high resolution, or they have high sediment accumulation rates for the deep sea because of sediment being moved by deep sea currents and then focused into drift type deposits within these basins. And so we are effectively getting sediments that are being delivered by these icebergs, which are coming up through the Weddell Sea here and then melting out over our site. And then we're also getting sediments that are being deposited by lateral transport by these bottom currents that are, again, moving sediment from a large geographic region and concentrating at our site, effectively giving us this bigger picture of the Antarctic ice sheet. And so one of the things that we realized pretty quickly as we were drilling in Iceberg Alley was just how exceptional these sediment cores were. Finding areas that have long and continuous deposition near the Antarctic continent has been a challenge in paleoclimate research. And so we found some sites that are among the highest resolution and most continuous sites ever recovered near Antarctica. And on top of that, they have well-resolved magnetostratigraphy. So we have a really good sense of where these magnetic reversals were occurring, which gives us time control. And the sediments show a strong imprint of orbital forcing in their lithostratigraphy. And what I mean by that is that the sediments are characterized by alternations of sediments that are more diatom oozes or have more sort of biogenic fossils, and sediments that are more silty clays that have more material eroded off the Antarctic continent when the Antarctic continent was, or the Antarctic ice sheet was larger. And so, And so if you look at this plot going down core, this is a proxy for that change in the terrigenous versus biogenic sediments, or the between warm and colder conditions. And you can see that there is a cyclic variation in warm versus cold indicators at our site, or that reflect these orbital changes in Antarctic climate. So we saw these changes in sort of these orbitally driven changes in the lithology of our site, which likely reflect changes in the Antarctic ice sheet. So one of the first questions we asked ourselves was, do these lithologic changes track global ice volume? And so this is a figure from a paper that's now in review that is comparing a parameter in green, which reflects changes in the terrigenous content of the sediment. So it's showing these from our warm biogenic diatom oozes to our cold silty clays lithogenic sediments. And if you do a little stretching and squeezing of the signal, you can get a really nice match between that signal and the signal of our benthic delitino, which is that globally integrated ice volume signal, through all of these glacial cycles until maybe you get back to about 900,000 years ago, where that correlation maybe works, maybe doesn't, is maybe a little bit more ambiguous. So that's a pretty interesting observation. And so for my work, I took a step back and said, okay, so what if we don't assume that the two signals are synchronous? How can we address the similarity between these two signals and still be honest about our age uncertainty? Because really, our only good age control points come from the location of where those magnetic reversals are, in a way that's totally independent of the climate signal. And so to do that, we're going to first acknowledge that our age models have uncertainty, and that the timescales that we're correlating to are also dependent on assumptions. So we're trying to look at this from a relative stratigraphy standpoint. Two, we're going to focus on signals that operate on frequencies similar to or longer than the frequency of reversals. So for the last 3.5 million years, reversals occurred at fairly random intervals, but on average about 250,000 years. And so if you looked at those plots that I showed you earlier that showed the evolution of how strong the rhythms were, those frequencies were on the order of a couple 100,000 years. So we'll look at those. And then we'll take a closer look at the phasing of some of these climate signals around the magnetic reversals themselves, where our stratigraphy and our age control are the strongest. So this is a pretty terrible figure to show in a talk. So don't worry too much about it. All I'm trying to show here is that the analyses that we're about to go into are the result of a pretty incredible amount of data. And so these data come from 2 drill cores that are both over 300 meters in length, looking at data collected at centimeter resolution along the whole length of those cores, both reflecting those lithologic variations or the alternations between the biogenic and lithogenic sediments, as well as the paleomagnetic changes. And so the result here is that we have a pretty well-defined paleomagnetic signal. You can see the flips between the different polarities pretty clearly, and a well-defined signal that's representative of more than one site. So that tells us that we're looking at a regional signal and not just a signal that's specific to one location. This is what the age models look like. So when we show an age model, depth is on the vertical axis and age is on the horizontal axis. Our interpretation of the polarity at these 2 different drill sites with normal and reverse is on the vertical axis. And then the time scale that we're correlating to is up here. So these are age control points. We don't have very many of them, but this is a question of accuracy. This is a very accurate age model, if not very precise. The further we move away from these age control points, the larger that uncertainty becomes, or the more uncertain we are in time. And so if we properly quantify that uncertainty, we can propagate that through all of our analyses, which is what we tried to do here. So here it is. We'll talk now about the evolution of the Antarctic climate rhythms using just these paleomagnetic or magnetostratigraphic age models. And so here's what our record looks like in purple. And so this is it on age. The up direction indicates the warmer conditions or those biogenic sediments. The down direction indicates the colder conditions or when we have more terrigenous material coming off the Antarctic continent. And you can see that there are all these cycles in this record at high frequency, and at lower frequency, it varies at frequencies that look similar to how the amplitude variation of the orbital forcing varies. These are 2 parameters that are related to changes in Earth's orbit. On top here is the globally integrated climate signal, that this benthic delitino that we're going to be comparing to. And so you should see that the overall trends of these records look really different, but we're going to zoom in and look more at the rhythms or the beats at which these records are changing as they evolve through time. And so I'm going to show you again these plots that show us the evolution of how strong that beat is in specific frequency bands related to different changes in Earth's orbit. And so first we'll look at the obliquity or tilt forcing. This is the one that occurs at 41,000 years and should affect both the northern and southern hemisphere in the same way, synchronously in time. So it has these variations in the forcing that occur on timescales of about 1.2 million years. Here we're looking at the last 3.5 million years or so. So the globally integrated signal, this benthic delitino, suggests that the ice ages were responding to that orbital forcing until about 1.4 million years ago, where the 2 signals decouple. The climate system starts responding, acting differently than the orbital forcing itself. And when we plot up our parameter that's tracking the lithologic variations in Iceberg Alley in this area called Dove Basin, which is where we drilled, you can see that while the amplitudes are a little bit different, the time variations are similar in Iceberg Alley as they are in the globally integrated ice volume signal. So that's what we might expect. We might expect if the southern hemisphere and the northern hemisphere were doing the same thing, that the southern hemisphere would look like the globally integrated signal. So that's pretty cool. That to me, that's a really interesting finding. We can do the same thing thinking about eccentricity. So this is how elliptical the Earth's orbit is. This is the globally integrated ice volume signal again. And we can see this transition that kicks off about 1.4 million years ago, and then having a very strong rhythm at 100,000 years within the last 700,000 years or so during this normal polarity chron. And if we look at our Iceberg Alley record, how the lithology in Iceberg Alley has changed over the same time, we see a signal that looks really similar, where we have an increase in that 100,000 year period that kicks off around the same time, and we have strong 100,000 year variations that occur during this normal polarity chron. So again, that's really interesting. That's telling us that lithologic variations in Iceberg Alley, which reflect Antarctic dynamics, looks a lot like the globally integrated signal. So nothing too crazy yet. But here we're going to look at precession now. So remember, precession might be a little bit more complicated, because if we think about this antiphase hypothesis, the prediction of that is that the northern hemisphere is going to be responding differently to this forcing than the southern hemisphere, and those two signals might cancel each other out through destructive interference if they're occurring in similar ways, or if ice volume is occurring in similar at similar amplitudes in both hemispheres. And so if we look at the Benthig-Delitino record, we can see that precession forcing, that response in the climate system really kicks off after that 1.4 million year transition. And looks like the orbital forcing. And before that, that signal is really muted. But if we plot up our Iceberg Alley record, we see that the Iceberg Alley lithology has been beating to that precession drum for the entire duration of its record, this 3.5 million years or so. There's just as much variability in that frequency band if you go back 2.5 million years ago as there was if you look around 1 million years ago, with some variability along the way. So that's a pretty interesting observation too. And it suggests that while the Iceberg Alley lithology looks like global ice volume at the other two rhythms, it looks really different at this one. And so to summarize that, Iceberg Alley lithology, which is this reflection of Antarctic climate, looks like global ice volume at 41,000 at the 41,000 year period. And suggests that the ice sheet variations in both hemispheres at obliquity timescales are acting synchronous with each other, as you might expect based on theory. The interesting thing is that Iceberg Alley lithology shows a lot of power or a lot of variability at the 19 to 20,000 year frequency band that's missing in global ice volume, which suggests that the Antarctic ice sheet may have been sensitive to these changes in the intensity of summer solar radiation at high latitudes in the southern hemisphere. And that signal might be canceled out, and we might not be able to see that signal in the earlier part of the record in that time period before 1.5 million years. But that's all very difficult to understand. And we're looking at something that's varying on a pretty short frequency. And so the next step was to zoom in and take a look at how those signals compare in detail once we look at the magnetic reversals themselves, where our stratigraphy and age model are the tightest. So here I'm plotting up three what we call subchrons, or very short polarity intervals that occurred before 1.5 million years ago, where we think that there might be this missing precession signal or precession response in the Antarctic ice sheet. And we want to look into that a little bit further. And so first, what I've plotted up here, these are our proxies for the polarity of the Earth's magnetic field at our site here in the second row down, and then at a reference site from the North Atlantic above it. And you can see that we've aligned these changes, these records only at these yellow lines to align those magnetic reversals. The great thing about this record in the Northern North Atlantic is that it has, in addition to having a beautiful paleomagnetic record, it also has a beautiful record of benthic oxygen isotopes, or Del 18O, this record of globally integrated ice volume. So we see how those changes in globally integrated ice volume relate to the position of where those reversals occur. So remember, wherever we go, we typically find the reversals at the same position relative to these climate events. And then here's our record from Iceberg Alley down off of Antarctica, showing this alternation between more biogenic sediments plotting up, indicating warmer time intervals, and more lithogenic sediments plotting down, indicating greater contributions from the Antarctic ice sheet. And then here are some of our orbital curves, just to give you a sense of the time periods in which they vary, both in the tilt of Earth's orbit as well as the intensity of solar radiation in the summertime. That's being controlled by that sort of precession or wobble pacing. And so the main takeaway I want you to take from this is that if you look at where the position of that magnetic reversal is relative to the change in the oxygen isotopes, it doesn't look like, these two records don't look like each other at all. There's variation within the subchron that seems to be consistent with shorter period variation, like you would expect from the precession pace variations. This is perhaps the best documented at this reunion subchron here, which is a beautiful subchron because it's very short in duration, and its duration is almost exactly one of these precession cycles in duration. And so you can see that this signal from Iceberg Alley, this Antarctic signal, doesn't look like the globally integrated ice volume signal, and that its variability is consistent with precession pace variability. So again, suggesting that during this time period, there is a precession signal in the Antarctic record that's missing in the globally integrated signal. And finally, we have one more subchron. These signals also look slightly different from each other, but the overall amplitude is fairly low here, and this is an interval that we're going to have to dig into a little bit more to figure out exactly what that pacing is. So now here is the final figure that I'll show you. It's now looking at magnetic reversals that occurred after that transition that kicked off around 1.4 million years ago. So starting at this here, we're looking at from 0.95 million years to about 1.2, and here we're looking at about 0.8 million years ago. And the takeaway here is that after that transition, we start to see that at these magnetic reversals, the Iceberg Alley lithology starts to look a lot more like the globally integrated signal, except at this one notable exception here. And so it's like all these other indications that we're seeing. It seems like around this time, the rules of what's going on change around 1.4 million years ago. So the main takeaways here is that there were likely intervals in the early Pleistocene before 1.5 million years ago, which is classically called the 41,000-year world, where Antarctic climate and likely the Antarctic ice sheet varied at 19 to 23,000-year periods, suggesting sensitivity of at least parts of the Antarctic ice sheet to local southern hemisphere peak summer insolation, and that this is a signal that's not captured in benthic Del 18O. So it tells us something about the evolution of the sensitivity of the Antarctic ice sheet to climate forcing in a way that we haven't been able to see before. We also see that the Antarctic climate indicator, as recorded as these lithologic variations in Iceberg Alley, starts to vary more like global ice volume during the transition, and then after the transition to larger overall global ice volume and 100,000-year pace variations. So like a lot of science. This is just the beginning. These were just some of the initial observations, the initial exciting observations from our expedition. And we've got a lot to look forward to, including a new NSF-funded project to dig into these records a little bit more, and address two main things that'll help us better understand how the Antarctic ice sheet varied on these sorts of timescales and what the Antarctic ice sheet has been sensitive to in the past. So first, we'll be working to improve the resolution and precision of our age models through some other novel techniques in ways that are independent of climate variation. So we can make these comparisons with as few assumptions as possible, like I was showing you in this talk. And then we're going to dig a lot more into making more direct connections to how these iceberg alley lithologic variations relate to changes in Antarctic ice sheet volume and dynamics. So with that, I'll say thank you for your time and for listening to me speak. And if anybody has any questions, I'm happy to stick around for a little bit and answer them.
I'll start with one super easy one. What led you into science in the first place?
Yeah, okay, that's a great question, and I actually don't have a direct path to marine geology. As an undergraduate, I was actually a business major, and thinking that was just something practical and a good career, and so I worked a little bit in that field afterwards, and I really didn't like it. So I went and did a 2-year term with the AmeriCorps, where I got to work with on a lot of environmental issues and with land management organizations, and that encouraged me to go back to grad school, or after taking some courses in earth sciences. And during that time, I just started to fall in love with paleoclimate and how you can use the Earth's magnetic field to better understand past variations in Earth climate, and I just kind of stuck with it, and here I am now.
Well, so here's one that I was thinking of, that as a conodont paleontologist back in the day, I had a couple folks that I hung out with that did do some paleomag, hard rock versions, and were so careful about orientation and making sure everything was spot on as far as orientation. How do you deal with that off of the core, out of the sediment core? Or is there something different about that? You don't have to worry about it.
Well, that's a great question, and it's actually a huge challenge because if you remember that animation, when those core barrels go down the pipe, they're spinning in every which direction, right? So when the core goes into the sediment, we actually don't have a good sense of where that core is oriented to north and south. The nice thing, though, is that at high latitudes, like working around Antarctica, the magnetic vector, you also get a lot of information from whether the magnetic vector is pointing into the Earth or out of the Earth. And we can measure that really easily because we know where the core is oriented relative to the up-down direction. So at high latitudes, we often just use that one parameter, which we call inclination, which is that change from if it's pointing in or out of the Earth. But the International Ocean Discovery Program has done some great work recently on installing and improving instruments to measure the absolute orientation of the core as it enters the sediment. And so when you're working at lower latitudes and the field is more horizontal, that tool is going to be really important for helping us do similar magnetic stratigraphies at low latitude.
Cool. Dallas, any chance that we've got anybody that's asked any questions through the chat rooms or chat boxes?
I haven't seen anything on Facebook.
All righty, sir. So I actually only just jotted down one more. So short question night for you, Brendan. For any high school or community college students that might be out there now or view this later, do you have any suggestions on what would be in their best interest as far as preparing for STEM fields STEM pathways in academia, might be coursework, might be other opportunities. And I know you kind of mentioned that's right, kind of at the kickoff of your talk as well, or at least that's one of the things I interpreted.
Yeah, I mean, I just recommend trying to explore as much as possible in different fields, take as diverse a course load as you can in different aspects of science to see what you like the most. You know, for me, I'm someone that came to marine geology a little bit later on than a lot of my colleagues. And it was, you know, I think it was as soon as I started to be exposed to it, I realized how much I was interested in it. So I would definitely say, try to get that breadth while you have the opportunity of a lot of different fields. And then if you find something that you're interested in, I'd recommend trying to reach out to see if there's a university near you where you can do a little work during the summertime in a laboratory and get some experience with some laboratory methods and working on some actual problems, and see how you like that, and maybe make some connections to faculty that are involved with research. Often schools will have programs to involve high school students or undergraduates from universities, you know, or colleges beyond, you know, just the one that they work at. So I would definitely explore some of those opportunities. Research can be a really exciting way to getting involved in a research project and doing a little lab work.
Definitely. Well, I want to thank IODP for putting together the lecture series that they've been doing for many, many years now. I'd also like to thank you personally, Brendan, for making time in your schedule to join us. I wish that we could have hosted you here, and definitely wish we could have hosted you in one of the either New Lecture Hall or the Hale Center. But one of these days in the not too distant future, hopefully we'll get back to being able to get back to some live talks again. In the meantime, I've already told you it's going to be virtual for winter for sure. Hopefully you'll be able to join us on the Cascadia Anniversary Talk, January 26th at 7 p.m. with Dr. Chris Goldfinger. Since I won't be seeing you in 2021, I wish you all the best for 2021. Any of the holidays you may or may not be celebrating. Most importantly, please stay safe, and I look forward to seeing you again in 2022. Take care.
Great. Thanks, Ron. That was
Thank you,
fun.
Brendan.